All right, so this is the second of a series of lectures on limits. In the last lecture, we talked about basically what is a limit, a little bit about the notation, the two different types of limits, left-handed and right-handed limits. And we talked about these from two different perspectives, looking at a graph and looking at a formula. And then we even touched upon the actual definition of a limit, and I did an example for you using that definition. Today, we're going to talk about limits at infinity. So let me start with a little bit of notation. So when we write down limits at infinity, there's sort of two limits we can talk about. The limit as x goes to positive infinity of f of x versus the limit as x goes to a negative infinity of f of x. So these two statements ask two questions. This top one here is basically saying what happens to this function as x gets larger. Where is the function going? So as a simple example, here's my x and here's my y-axis. And if I have my function here, f of x, and it's going, let's say it comes up, and it comes down, and it heads towards 0, like that. So y equals 0 is going to be a horizontal axis. So the idea is as x goes to infinity, as you go all the way to the right, this graph is getting ever and ever closer to the height of 0. So this would be equal to 0. Whereas at negative infinity, it looks like it continues to go down. So as you go to the left, the graph continues to go down, down, down forever. So we'd say it equals not positive infinity, but negative infinity, because it's going down, 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 down. So that's sort of the two types of limits we're going to work with today. So let's look at an example involving a graph. And so down here I have a bunch of different limits, and I want to use this graph to answer these questions. So this first one says, what's the limit as x goes to negative infinity of f of x? So negative infinity, remember, infinity is sort of like a concept. It's not really a number. It says basically what's going on all the way out to the left here. And so you look all the way out to the left and you see that the graph, the height of the function, is approaching the number 1. So this would be 1. Because as you go to the left, this is getting closer and closer, and this is supposed to be a horizontal asymptote. There's two types of asymptotes. We have horizontal asymptotes and vertical asymptotes. Basically, the idea of an asymptote is that the graph approaches it but never actually hits it in the end. The limit as x goes to negative 1 of f of x. So you got to go find negative 1. So let's find negative 1 here. So here's negative 1. And if you look, the actual height is 3, but that doesn't really matter for the limit. What the limit cares about is what happens about negative 1. So from the left of negative 1, it looks like it approaches height negative 3. And from the right, so here is where I'm looking. From the left, it approaches height negative 3. From the right, it approaches height negative 3. So my answer would be equal to negative 3. And then in part C, let's change colors. I want to look what happens as x goes to 2, so the limit as x goes to 2 of f of x. Well, here's 2. And then from the left, it hits height 1. Whereas from the right, it's going to come down and hit height 2. And so because those two values don't agree, because the limit from the left is not equal to the limit from the right, we say that this does not exist. So we just write DNE for shorthand for does not exist. All right, so now we get into some left-hand and right-hand limits. So let's look at this one. So this is a left-hand limit. So the limit as x goes to 5 from the left of f of x. So up here you find 5. So here's 5. And as you come in from the left, you see the graph goes down, 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 forever going down, ever approaching this vertical asymptote x equals 5, but never actually touching it. And so the idea going down, 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 down would be equal to negative infinity. So this basically says, oops, I drew it in the wrong spot, negative infinity. All right, so what this says is that as you come to 5 from the left-hand side of 5, the graph is going to keep going down, down, down forever. Whereas when you come in from the right-hand side, the graph seems to be going up, up, up forever. And so you'd say this equals not negative infinity, but positive infinity. And then finally, the actual value of the limit at the point, well, because it's negative infinity on one side and positive infinity on the other, we say it does not exist. And then finally, we'll do a limit here as you go to positive infinity. So what happens as you go to positive infinity? And you can look at the graph. And so as you go out to the right, the graph goes down, down. Looks like probably ever closer to 0, but never actually hitting 0. So as you go out further and further right, as you go out to infinity, the height approaches the number 0. Find the vertical and horizontal asymptotes. So for vertical asymptotes, there's just one. It's right here. And so that's the line x equals 5. So let's just write VA for vertical asymptote. And then for horizontal asymptotes, there's actually two of them. One is drawn. So here's one horizontal asymptote, and that's y equals 1. Right, these are actually lines. X equal 5 is a vertical line. Y equal 1 is a horizontal line. And we have a horizontal asymptote, right here at x equals 0. You can't draw a dotted line on it because it's the axis. And so the axis is solid, so it would go over the dotted line. But x equals 0 is also a horizontal. Oops, not x equals 0. Sorry, y equals 0. Right, horizontal axes are given by y equals, are given by horizontal lines, where vertical axes are given by x equals because they're vertical lines. All right, so hopefully that sort of helps with the sort of concepts, the intuition behind what happens as you go to positive and negative infinity, and sort of reviews a little bit about limits. The next thing we want to look at is actually dealing with limits and formulas. This is a little bit, I actually don't think it's a little bit hard. Actually, this is a little bit easier because what we're going to start with first is just polynomial over polynomial. So we're going to look at these limits where we have some sort of polynomial divided by another polynomial. And when you're going to plus or minus infinity, it's actually really easy to figure out where the limit's going to go to. And remember, a polynomial looks like, one of these on top. It's just a nice sort of sum or difference of some numbers times some powers of x. And the powers are nice. There's no square roots. There's no negative exponents. The exponents are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nice natural numbers, basically. All right, so when you do these, it's actually real easy because if you're going to infinity, the idea is that a single term on top is going to dominate and a single term on bottom is going to dominate. And so really, when I look at these things, what I can cross off is all the lower degree terms lower than, in this case, 4. So I can actually just cross off those terms, and I can cross off on the bottom. Now on the bottom, I have to be careful here. The highest term is x cubed, so I can cross off the x squared term and the 2x and 1 term. And the reason I can do that is because I'm going to infinity. And so if you think about it, if you take infinity, a really huge number, and you take it to the 4th power, it's going to be enormous compared if you square it. I mean, just take 100. Right, if you take 100 to the 4th power and compare it to 100 squared on your calculator, we can do this, and you'll see that 100 to the 4th power is just huge compared to 100 squared, even though they're both big numbers. So on here, let's do 100 raised to the 4th, and I get that number, whereas 100 squared is equal to that number. So 100 squared is 10,000, whereas 100 to the 4th is, what is a comma, 100 million. So you really don't care about the 100 squared. It's sort of like chump change. It's like cents. I have $1 billion. Do I care if I have $1 billion in 1 cent, $1 billion in 2 cents, or even $1 billion in $100? Who cares? All I care about is that $1 billion part. So the same idea sort of applies here. So when you're going to infinity, you can cross off all the lower degree terms, and what that's going to give you is the limit as x goes to infinity of 3x to the 4th. And this is me showing my work. You have to show your work. Right? The important part of this is how are you solving this problem, divided by 5x cubed. And so this is equal to then, of course, you're going to get some cancellation in the x's. So I'm going to get the limit as x goes to infinity of 3x divided by 5. And now I'm going to plug in infinity. So I have 3 times infinity divided by 5. And this is me thinking, you have 3 times a really huge number divided by a regular number. So this is going to be a huge number. So it should be equal to infinity. And I just realized there's actually a slight mistake on here. So I'm going to add an example. I'm going to call it another part A, because this example was actually supposed to be written like this. So x goes to infinity, and let's just change it a little bit. So 3x to the 4th minus x squared plus 1, all divided by, and over here then I'll have 5x to the 4th. So instead of 5x squared, that was actually supposed to be, 6x. 6x to the 4th. And then plus, just copy this down, 5x cubed minus 2x plus 1. So we're going to add an extra example. I guess we can call this D, then I can have, say, A, B, C, and D. So now how would I do this one? So you follow basically the same pattern. Cross off what they have in common. So, the lower degree terms. Okay, sorry. So we cross off the lower degree terms. So x to the 4th, those are lower degree. Now x to the 4th down here. So cross off the lower degree terms. Those are going to be gone. And so I'm going to have the limit as x goes to infinity of 3x to the 4th over 6x to the 4th. And of course, x to the 4th are going to cancel on top and bottom. So this is going to be equal to the limit as x goes to infinity. And I have 3 over 6, which of course, when I plug in infinity, there's no place to plug it in. So you're just going to get over 3 over 6, which is just equal to 1/2. So my answer for this one would be 1/2. Whereas the answer for the top one, when the degree on top was bigger than the degree on bottom, you got infinity. Now what happens if you switch that? So if you look in part B, in part B we have the degree on bottom is bigger than the degree on top. And so again, because I'm going to infinity, in this case negative infinity, I can cross off these lower degree terms because basically the highest degree term will dominate in the end. And so this is going to be equal to the limit as x goes to negative infinity of, I'll have an x cubed on top divided by an x to the 7th on bottom. And so that's equal to the limit as x goes to negative infinity. And then, you get some x's canceling. So you have cube up here and 7 down here. So you're going to get 1 over x to the 4th. And then I'm going to try to evaluate my limit. Evaluate your limit is a fancy way of saying plug in where x is going to. So this is going to be equal to, I'll put it in parentheses, 1 divided by, quotes, negative infinity to the 4th. Because this is basically me thinking. And so this is equal to 1 over, and then negative infinity to the 4th is just basically infinity. So the idea of infinity is like a really big number you can't possibly ever imagine. So if you take it to the 4th, it's still a really big number you can't possibly imagine. And of course, a negative times a negative times a negative times a negative is a positive. And again, this is just me sort of thinking. And 1 over a super huge number is like the number 0. And so I get out 0 here. And so these are basically the 3 cases. So you have case 1, case 2, and case 3. Because if you think about it, polynomial over polynomial, what could happen with the degrees? You could have the same degree in top and bottom, which we did here, so x to the 4th, x to the 4th. And in that case, it's just this coefficient divided by that coefficient, which is 1/2. You could have the degree on top smaller than the degree on bottom, so that would happen in case 2 here. So it had degree 4, case 3. You had 3 on top, degree 3 on top, and degree 7 on bottom. And in that case, the bottom basically dominates, so it goes towards 0. And then case 3, okay, the last case we're going to talk about is the degrees bigger on top than it is on bottom. All right, so I guess I should reorder these since I went in that order. So case 3 here, you have degree bigger on top than bottom. And in that case, the top is going to dominate, which means it's going to go off to plus or minus infinity. In this case, it went to plus infinity. And in fact, let's do part C, and we can actually tweak part C. Instead of going to positive infinity, let's make it go to negative infinity. And so if you do this one, and let's rewrite it down here because I'm running out of space. So let's just rewrite this. This is going to be, we're going to do the limit. We're going to change the problem a bit. Let's do the limit as x goes to negative infinity of x to the fifth minus this 3x squared plus 7x minus 10, all divided by x to the fourth plus 2x cubed plus 7, which is equal to, so in this one, because I'm going to negative infinity, and this is only because I'm going towards an infinity, I can do this. It doesn't work if the limit is x going to 2 or x going to 0 or x going to 1. Because it's going to infinity, I can cross off all these lower degree terms. So the highest degree term is a 5, so I can cross off x squared terms, x terms, and constants. Same thing down here. Because it's x to the fourth, I can cross off the x cubed and the 7 and the constant 7, and I get the limit as x goes to negative infinity of x to the fifth divided by x to the fourth. Of course, then x's cancel, so this is going to be equal to the limit as x goes to negative infinity of x. Let's evaluate our limit, meaning plug in that point, so I get negative infinity. And I don't need quotes there. All right, so this is just equal to negative infinity when you plug it in. So that's an example where you don't get out positive infinity, you got negative infinity. And basically what it's saying, so important to actually try to interpret what's actually going on here. If this is my function and you look all the way to the left, it's going to continue to go down. So whatever this function's doing, I don't know what it's doing over here, but I know if you go to the left, it's going to wind up down here. It's just going to keep going down. Whereas, let's take a look at this function here. Right, so if you look at this one right here, as x goes to infinity, it's going to approach 1/2. So that tells me I have no idea what's happening around over here, but as you go farther out to the right, it's going to approach, so here's 1/2, it's going to approach this asymptote 1/2, either from the top or the bottom. I don't know. I have to do a further analysis to figure out if it's from the top or from the bottom. But I know it's going to approach this horizontal, I don't know if I said vertical, it should say horizontal asymptote of 1/2. Right, so this is y equals 1/2. So that's the idea. And these are real simple to do in the end because you can just look at the degrees and compare them. But you have to show your work. There are more complicated ways to do these, and I try to give you the easiest way, but I still need you to show your work so I'm sure that you understand what you're actually doing. Let's look at a couple examples where they're not just polynomial for polynomial. So let's start with this part A here. So on this one, what's the idea? So you have a polynomial on top, and on the bottom you have the square root of 9x to the fourth plus 1. You can still use the same idea we did before. On top, as you go to negative infinity, the x cubed term is going to dominate, so you can cross off the negative 3, because it's going to be like negative a billion squared take away 3. Who cares about the 3, right? Same thing down here. It's going to be like 9 times negative a billion to the fourth, and then you add 1 to it. Who cares about the 1? So you just kind of cross it off because you're going to negative infinity. And so this is going to be equal to the limit as x goes to negative infinity of x squared divided by, and then I have the square root of 9x to the fourth, which is equal to the limit as x goes to negative infinity. And now x squared on top, and then I can take the square root of 9x to the fourth. That's going to be 3x squared. And so then this is going to equal, so I'm showing my work, right, one step at a time. X goes to negative infinity. Now x squared is going to cancel. I'm going to get 1/3. And so now I'm going to evaluate my limit, and it's just going to be equal to 1/3 because there's no place to plug in infinity, so you just get back the constant 1/3. I should mention that you can always check your work on these by plugging in a point close to where x is approaching. So like if x goes to negative infinity, maybe I'll plug in, I don't know, negative 1,000. So if you plug in negative 1,000, so I'll have negative 1,000, and I better do this like this. So negative 1,000, and I'm going to square it, so raised to the 2. and then take away 3 in parentheses. So there's a top, divided by, and then the second square root of, then I have 9 times negative 1,000 in parentheses, raised to the 4th. And then I add 1 to it in parentheses. And if I hit enter, I hope I get out something close to 1/3, which I do, 0.3333233. And if you remember, 1 divided by 3 is 0.33333 without the 2 there, but it's approaching a limit. The idea is as x gets closer and closer, it goes, in this case, further to the left, where does this thing approach? And it's going to approach 1/3. So you can always check your work on these with your calculator. You can't necessarily always use your calculator to do these, right? But you can use your calculator to check your work. Now this one's kind of interesting. So the limit as x goes to infinity of sine of x, what are you going to do for this? And so the idea behind this, there are 2 ways to do it. One, you can draw a graph of what the sine function actually looks like, and you can use that to kind of figure out what's going on. So as you go out to infinity, the sine function just goes up and down, and it goes up and down forever. So forever going up and down. So the idea is if you look far, far, far out to the right, as you go to infinity, what does the sine function do? Well, it continues to go up and down between -1 and +1. So it never actually settles on anything. So it never actually approaches any number because it keeps going up and down between -1 and +1. So because of that, we say this limit does not exist. So that, and the reason, if you can see it here actually, I mean, it just keeps going up and down. So there is no limit. It's not approaching anything. It just keeps going between -1 and 1. You could use your calculator too and start plugging in really big values for x, and you'll see that as you plug in bigger and bigger values, it does not go to any certain number. Now the one below it's a little bit different. Right? So the limit as x goes to infinity of sine of x over x. Now if you think about this, what the sine function does, it always goes between -1 and 1. And then x down here is going to go off towards infinity. So basically, on top, it's going to be bounded between -1 and 1. And on bottom, it's going to be unbounded. So the bottom's going to blow up, whereas the top's always going to be some number. And so this is actually going to be equal to 0. So if I was doing this, there are 2 ways I can do it. I can think about it like this. I could say, okay, well, if I plug in, this is me thinking sine of infinity over infinity. I know the sine is always between -1 and 1, and infinity is just a huge number. So if you put some number between -1 and here and 1 and divide by an incredibly big number like a billion, you're going to get out something like 0. So that's me thinking. I can also make a table for this to show my work, and this is one I often do. So I can do an x and then a sine of x over x, and I can just plug in a really big number like, let's do 1,000. And on my calculator, I can do sine of 1,000 divided by 1,000. Make sure you close that parenthesis off on the sign. And I get 8.268795405 capital E to the -4. So what that means is basically this is going to be 8.27 times 10 to the -4, which is equal to 0.0008. The negative means move the decimal to the left 4 spots, 27. Make sure I copied that down right. All right, so and that's basically 0. And you can plug in, if you want, 10,000. Just for fun, let's do it since it's not too hard to do on my calculator. So I add a 0 here, and I add another 0 over here. And you'll see you get even closer to 0. Now it's negative, which is fine. Right? This is just going to be equal to negative 0.0000, 4 zeros, and then a 3. It's still closer to 0. So this would be equal to negative 3 point, let's round it to 06 times 10 to the -5th, which equals negative 0.000306. So that's the idea. So this limit is actually equal to 0. Now, same thing's going to happen here. Now, for this one, basically there's very little I can do algebraically, and even the graph, I'd have a hard time probably getting to graph appropriately. So I would do a table. Right, so the idea of a limit, this is just basically asking a question. As x goes farther and farther out to the right, what is this expression? What does this function do? Does it approach a number? Does it blow up to infinity? Does it blow down to infinity? So figure it out. So you can use your calculator. And I'll start with let's start with 100 and see what happens. So on my calculator, I'm going to plug this in. So let me write it down. I'll do 1 plus 1 over 100 to the 100. So I have left parenthesis 1 plus 1 divided by 100 in parenthesis raised to the 100. And I get out this 2 point, and I'm going to copy it all down. So 2.7048, and then 13829. 13829. And so I get that one. Then I could do 1,000. So I'm not going to copy down what I'm going to put in. I'll just put it in my calculator. So I'll just hit second entry, and I'll change that 100 to 1,000. And I'm going to see if I can't figure out what this number actually is, because I have no idea. But if there is a limit, it should be approach something. And then I get this 2.7169 239. I think it was 32. Okay, and I still don't know what it is, so I'm going to plug in. I'm getting tired of plugging in stuff, all right? So I'm going to plug in, what's this, 1,000,000? So let's plug in 1,000,000 and see what happens, and hopefully that'll give me the answer. And so I'll hit second, enter. I have 1,000, so 3 more zeros, and then I want to come back up here and add 3 more zeros. So there's 1,000,000, hit enter, and now hopefully that number is starting to make sense. I have 2.718280469. And if you remember, if you hit second, e to the 1, you get out almost exactly the same number. And so this is actually supposed to go to the number e. All right, just by watching what happens as x gets bigger and bigger. If you make it equal to 1 billion, you'll probably get a better approximation according to your calculator, what your calculator has stored for e. And so I think this wraps up pretty much our lecture on limits at infinity. So let me just review real fast. All right, so we talked a little bit about this notation. The new notation that we introduced is this limit as x goes to infinity of f of x. The limit as x goes to infinity of negative f of x. A few things. Don't ever just write the limit as x goes to something equals something. There needs to be a something right here. It turns out the limit's actually an operator. It's actually, in some sense, a function on functions. So if you say the limit as x goes to infinity of what? Something has to go here, so don't ever leave it blank. We talked a little bit about the graph and the formula and how this sort of in behavior and asymptotes. In behavior is basically what happens in the end. What happens as you go to infinity? What happens versus you go to negative infinity? What happens on the very left-hand side? What happens on the very right-hand side? And we talked about these vertical asymptotes and horizontal asymptotes.